How's everyone doing today?
Pretty well.
Y'all ready? So I've been doing more videos for the homework solutions, and I finished up 10.5 today. I think it's 4 videos, probably like 3 hours worth of video. So 10.5 is where things start to really kind of pick up. I told you that. So just so you know, it's out there. It's available to you. We haven't talked about it yet, but it's been fun. I'm enjoying making these videos. We're gonna do. Yeah, it's gonna get real tough later. It's gonna be a lot of work, but I guess it's a one-time thing. If I do all the videos, then I don't have to do it again, and then they're gonna come change the book, and it's all gonna be screwed, right? I'll make sure I get myself on that committee so that we don't get switched. Okay. Let me silence my phone. I apologize. Come on. Okay, so I have a quiz for you today. So please take this. Do not put your name on it. I'm kidding. It's not a quiz. It's a survey. Okay? Do not put your name on it. So take one, pass these back. I'll give you plenty. It's real quick, okay? I don't want to take much time at all. Maybe just like 2 minutes tops. Is there any extras here? Oh, there's more coming. Got more over here?
Oh,
A lot over there.
yeah.
Thank you. So I want you to answer for yourself, which, if this indicates how you feel. I've been watching the videos, recorded lectures, and find them useful. Yes or no? Circle one of those. And if you want to make any comments at the end, you can, since I don't know who you are. If you want to say, hey, this is really terrible, or if you want to say, hey, I like this part of it, or you just don't want to put anything, I don't care. Just want to give you an opportunity for feedback. When you're done, just kind of get them all clustered up at your table. We're just going to put them all together, and then I'll collect them. If your whole table's done, let me know, and I'll come pick them up. All good? I hope that you're giving honest feedback here. Because I don't know who you are. If you're sitting there saying, yes, I've done all the homework, and you haven't, I'm not quite sure why you would do that. Then you're lying to yourself, basically. Yeah, if you circle all yeses, that's not a good thing, is it? Anyone else? Okay. All right, can y'all just hand that over here? You missed the quiz. Here, just turn that in at the end of class. All right, let's proceed. So we left off last class. We were talking about 10.3 dot product, right? And I had done this problem. I know some of you probably watched the videos of the lecture. Maybe you looked at it. Did anyone notice the difference in the color? Like it was brighter? Anyone notice? Even notice it? No? A little bit? It's still a little dim, but think that's the best I'm going to be able to do. But it's legible. I mean, you can see it, right? Okay, that's the most important thing. Okay, so that's where we left off. And now we will continue. And we have another result of the dot product theorem that is very useful, especially in three-dimensional space. This is a formula that allows us to find the angle between any two non-zero vectors. And this comes directly from the definition of the dot product, which we did last class. It was u dot v equals magnitude of u times magnitude of v. That would have been a good quiz, right? Give me the formula for the dot product and ask you to like write the right side of that. That would have been a nice one-question quiz, right? Now, if we just take this and solve for theta algebraically, we get that formula, right? Just divide both sides by these two, right? And then you have cosine theta equals the dot product over the magnitudes, and then take arc cosine on both sides, and you get this formula, right? So there's nothing new here. It's not like, hey, this is a brand new formula. It's just solving for theta here. You understand? Now, it's important that they're non-zero vectors. I did not put that here, all right? I should have. Because what happens if u is the zero vector? It would be, yes, but what would happen in this formula if u or v was the zero vector? You'd be dividing by 0 because the magnitude of the zero vector is 0. So you'd have division by 0, it wouldn't be defined. So technically this should say two non-zero vectors. The angle between two non-zero vectors can be found using this formula. All right. So we're going to find the angle between these two vectors. Right here. Keep in mind throughout today that all of this, I said this last class, everything we're doing is just kind of putting tools in our toolbox. We're going to pull these tools out later, right? There's no way I would ask you a question like this on the in-class test. This is way too fundamental, all right? But like the problem I did today in 10.5, I had to find the angle between two planes. So I had two planes in three-dimensional space. I had to find the angle between them. To do that problem, you have to be able to do this. So that's more like the in-class problem would be. But we have to know how to do this. So we have two vectors sitting in space, right? So like we've got this vector u sitting here. It's three-dimensional. We got some vector over here, you know, v sitting in three-dimensional space, right? And what we're doing is trying to find the angle between them. So imagine just taking this one, sliding it around. Remember, you can go up, down, left, right. Just don't change the angle or the length. And we can just attach them tail to tail. And then what we're looking for is the angle between the two. So we're trying to find this theta. Now, the reason I put it on the board is because I think it's easy to see that way. But in 3D space, you know, these could be pointed out that way and this one this way, and then we have to slide them and get them like that. And then the angle we're talking about, remember me showing this to you? You just have to look at them like in a flat plane, like this. And if you look at it that way, then we're looking at that angle in there. All right, so. Okay, so it's just a straightforward computation. We need to find theta, which is arc cosine, hope you brought your calculators, of u dot v over magnitude of u times the magnitude of v. So let's go about getting all these things on the side here. What's u dot v? So this is gonna, when we multiply this, am I gonna get a vector or a number? Number. Okay, so I take the first component of u, multiply it times the first component of v, -6. I add to that the second component of u and the second component of v, which is 28. I add to that third component times third component, so that's 4. And what do we get there? 26. All right, so that's going to be this numerator, right? And then I need the magnitude. So magnitude of u is the square root of the sum of the square of the components of u. So I just square each one of these, add them all together, right? Then take the square root. So 4 plus 16 plus 16, 36, which is 6, right? Any questions where I'm getting those? If you did your homework, then you've done this already, right? You've done all these smaller pieces. Magnitude of V is what, 9 plus 49 plus 1, which is root 59, which isn't a perfect square, so I'm just going to leave it like that. And then I'm ready here. So I'm going to write cosine inverse, or arc cosine, of the numerator, which is 26 over 6 times root 59, and you get your calculator out. And we're going to get an approximate answer here. So we'll use decimals, and let's make sure we're all in. You want to do degree mode? Degrees usually make a little more sense when we're trying to visualize it. Hey, can anyone tell me quickly, without doing the computation on your calculator yet, whether or not the angle between them is acute or obtuse, and why? Is the angle less than pi over 2, less than 90 degrees, or greater than 90 degrees?
Less than.
Less than, why?
Because the dot product is positive.
That's right. We know the dot product is positive. That tells you that the angle had to be between 0 and 90 degrees. So we already know it should be an acute angle. So if we get this answer on our calculator and it comes out to be 102 degrees, something's wrong, right? Something is wrong. So let's do this. 26 divided by 6 times. Shit. Someone give me an answer. 55.6, 55.7, somewhere around there. So this right here equals approximately 55.7 degrees. That was supposed to be a little squiggly equals. We good? We move on? Okay, so what if someone gives you two vectors? Are those the same vectors? No. No, they're not. And you're asked to determine whether or not they're orthogonal, parallel, or neither. So you're given two vectors that live in three-dimensional space, and you want to know if they're parallel, which would mean what? What would it mean for them to be parallel? They're pointing in the same direction. It could be like this, though, right? So the technical definition of parallel meant scalar multiples, right? They're scalar multiples. Orthogonal would mean that what? They're perpendicular, which means that the dot product would have to be 0. And then neither would be, well, neither one of those cases are true. So what we're going to do is we're going to check for parallel. If it doesn't happen, then we check for orthogonality. If that doesn't happen, we say neither. If we get parallel right off the bat, then we're done. It is parallel, isn't it? Okay, so I'm going to check for parallel. So what I need to know is if I take u and scale it, right, multiply, not dot product, scalar multiplication, is there a way that I can get v? Or it could be the other way around. Can I scale v and get u? Either one of those. So can you tell just by looking? Yeah? If I multiply u by what number? -2. So this is just a visual inspection. If I take -2 times u, that's a -2 times the vector 2, -2, 6. And then if I scalar multiply, which means almost like a distribution through the vector, we get -4, +4, -12, and holy crap, that's v, isn't it? So they're parallel. What did we say about that number, though? The -2? It had to work for every one of those, right? Okay, which it did. So do we need to go on? No, we're done. They're parallel. It can't be parallel and orthogonal, can it? No. So what if you had decided to come in here and you wanted to check the orthogonal first before you did parallel? What would have happened? Let's see. So we're done, but what if we had wanted to check this? I'm going to use that for orthogonality, that symbol, perpendicular like this. Okay, so I'm checking, are they perpendicular? So what would you do? Dot them? Dot them, right? Just dot them up and hope for 0. Do we get that? So here and here we get -8. We add to that -2 and 4, -8 again. And then 6 and -12, which is -72, right? We agree? Do we agree with that? Okay. And is this 0? Not equal to 0. So they are not orthogonal. So that's if you would have started with that. You would have said, oh, wait, they're not orthogonal. I need to move on to parallel. And then you would have found that they're parallel. I got lucky. I checked parallel first. Any questions there? Straightforward? All right, the vertices, or the corner points of a triangle in three-dimensional space, are given to you by these things here. Is this a right triangle? I alluded to this last class. Showed you that there was an easy way to do a problem like this. So let me ask you first, what are these things right here? What are these? These are points in three-dimensional space, right? Not vectors? So let's imagine we have 3 points in R3, and I could go and try and graph them, and I'm not going to. I don't care. Here they are, all right? Let's label these points. How about A, B, and C? Is that okay with you? Then let's label these A, B, and C. And then I'm going to connect these together with little line segments. They form a triangle in three-dimensional space. All right? Does everyone understand? I don't really care where they are. Do you understand that? I mean, if I show you a triangle, let me show you a triangle real quick. In three-dimensional space, okay, you see it here? Here's my 3 points. There we go. Okay, you're looking at it from your point of view, this is what it looks like. But if you walk to a different part of the room, it's going to look like a completely different triangle, right? Or if you go down here and look up, or it doesn't matter where you are. So why does it matter for us? We don't have to get real critical about where this thing is. All we want to know is whether or not it's a right triangle, right? So what do you have to have in order for it to be a right triangle? At least one angle, right? At least one of the angles at the vertices, at least one of these has to be 90 degrees, right? Well, I guess you can't have 2 be 90, right? But you have to have 1 be 90. So how should we do it? You could find the lengths. You could find the distance from here to here, distance from here to here, distance from here to here, and check Pythagorean theorem, right? That's one approach, but that's the harder approach. You could dot product things, couldn't you? We know that dot products check for orthogonality. But you have to dot product vectors, right? You can't dot product points. Yes? So let's label some stuff here. I'm going to call this angle right here little a, this angle right here little b, and this angle right here little c, as opposed to my big C. There's my big C. If I'm interested in angle A, I'm going to have to realize 2 vectors and dot them, right? The vectors that I need to realize are here. Is first the vector that connects these 2 points together from A to B, and the other vector would connect A to C. Do you see the blue vectors? Those I can dot. So why don't we call this vector over here the vector AB, and the vector up here, let's call it AC. How about that? See the notation? Questions? So what we're doing right now is we're checking the angle A. Right? That's what we're doing right now. And to do it, I'm going to dot product the vector AB with the vector AC. And hope to get 0, right? If I get 0, then they're orthogonal, and it's 90 degrees, and I'm done. It's a right triangle. But I need these vectors, don't I? So you have to actually get the vector. So what is the vector AB? What is the vector from the point A to the point B? So you remember how we did this, right?
1 minus 2.
Do we do 1 minus 2 or we do 2 minus 1? 2 minus 1. Okay, so I'm going to do 2, take away 1. That's going to be the first component of this vector. I'm doing this one right here. So 2 minus 1 is 1, so 2 minus 1. And then 0, take away negative 3, which is positive 3. And then lastly, what? 4, take away negative 2, which is 6. I'm going to dot that with the vector AC, which I am going from A to C. So I take this and I subtract this. So what's the first component of the vector AC? Anyone? Negative 7. Next component, anyone else? 1. Next component, negative 3. And now the dot.
Are we sure the second component is
I don't know. I didn't even look at it. Did you all agree with it?
2 minus?
It's negative 2.
Oh, yeah,
Take away negative 3, so it becomes a plus 3. So it's good. So we're all agreeing on this? Any questions? Yes?
So, can you tell me if we're going from A to B?
Mhm.
That's what we. So that's what we do. If we're going from A to B, we take B and
Subtract A.
subtract A.
Yes.
Just making sure.
But let me point something out. We discussed that last Wednesday. So I'm not calling you out, okay, because I know everyone is going to have questions. But you can't walk in here a week after we talked about how to do this and still be confused on it. This class, just like Cal 2, you'll get wiped out. You've got to keep up. This can't be a question. It's okay to question, okay, because it's the beginning, all right? But if each of these little things becomes such a trivial little piece of a bigger problem, if these things are hanging you up, man, these problems are going to take forever, and they're going to be very difficult. So you want to really make sure, like if you're confused about this, just do a bunch of problems, practice, and then it'll become second nature at some point. But I know you're not the only one, because I could tell by looking there are still people like going, which one minus?
I was just questioning myself because I thought it was the other way around, but then I see.
And when we talked about this originally, I think there was some confusion in the room, and I may have confused you when I lectured on it. What I do is I say I'm going to go from point A to point B, right? So I'm going to start at B and subtract A. That's what I'm going to do. That's the way it works in my mind. That's how I remember. I don't know. I don't try and go off a formula or anything. All right, so can we dot these? Negative 7, what? Plus 3, minus 18. And we were hoping for 0, weren't we? So it's not. It's not 0, right? So is it a right triangle? We don't know still, right? So what would I have to do now? Check another angle. Which means I have to draw 2 new vectors, don't I? So now I have to check angle B. So we start over, check angle B. And to do that, I'm going to have to redraw my triangle. And create some vectors. What vectors do you want me to use for the angle B. So I'm going to do B to C, right? BC, and B to A. Hold on. How is the vector from B to A related to the vector from A to B?
Negative.
It's just the negative, right? So we already did that, right? So using the fact that the vector from B to A is actually negative A to B, what was AB? I forgot. So I just changed the signs on all of them? So -1, -3, -6, right? So I have that one. But BC I don't have, right? I never looked at BC. So the vector BC from B to C is, so I'm going to go from B to C. So I'm going to start at C. I'm going to subtract the points from B. So start at C, subtract -6 minus 2, -8. And then -2, take away 0, -2. Then -5, take away 4 is -9. There's no way that's 0. Why? How can I tell without even multiplying? Yeah, this and this are going to be a positive, a positive, a positive. There's no way that we're going to add those up and get 0. So that's not it, right? It's not a right angle. So there's only one thing left to check. That's angle C. We good? BA dotted with BC is not 0 just by looking. So now we check angle C. So I'm going to come up with two new vectors. I'm going to go from C to A, and I'm going to go from C to B, which will be this way. And how is that related to BC? The opposite, right? Negative. So the angle, what's the vector from C to A? So start at A, subtract C. What is it? 7, -1, 3. And then the vector C to B is the opposite of this, right? So change this and make these positives. Am I going too fast or are you following this? You're okay? Dot those. CA dotted with CB is 56 minus 2 plus 27. It's not 0. It's not a right triangle. Now you may say, hey, look, I prefer to have just got the lengths and done Pythagorean. And I would agree, okay, yeah, that you may have been done, you like finished that already, right? You may have already been done. But once you get quick with this, creating the vectors, dotting them, once that becomes fast, then, you know, this isn't so bad. And also, you could get lucky. You have a 33.33% chance of picking the right angle. If there is a right angle, right, you have a 1/3 chance that you get it on that first shot. Whereas with the Pythagorean, you've got to do the entire work no matter what, right? All right. How do y'all feel about that? Okay? All right, vector projections. Everything that I'm going to show you on the board here, the animation, is two-dimensional, but everything I show you can be extended into three-dimensional. It's just easier to show it two-dimensionally. Given two vectors, we can project one vector onto the other. Look at it as casting a shadow of one vector onto the other. All right, so here's the picture. I'm going to start with this, all right? So I have a blue vector and a red vector, all right? Right now, what I'm doing is I am projecting the blue onto the red. So if the red one is pointed straight out to the right, and the blue one is up like this, then when I say drop a perpendicular, it's almost like just dropping a line straight down, yes? And if I drop that line straight down, it's going to hit right here on the red vector. And if I draw a new vector that goes from here to where I hit, that new vector is called the projection of the blue one onto the red one. Okay? But this red one does not have to be pointed out to the right. It can be pointed anywhere. So instead of me making it that simple for you, let me make the red one come up like this. Now, you still have a projection, but instead of dropping a line, straight down, what you're doing is you're dropping a line that is perpendicular to the red one. That doesn't look right. You know what? It's the scaling of the way that the projector is, and the aspect ratio makes this look different, but this should be a right angle right here. It should project down to a right angle. I'll have to, let me make sure on mine. Yeah, on mine it looks dead on, so it's something to do with the projection. So you have to believe that that's a right angle. If I click this, you'll probably believe it. There. Okay? That's what's happening. That's the projection of the blue onto the red. So it creates a new vector, doesn't it? This purple vector. But we could go and do it the other way. Or you know what? Let me do this. Let me make the red vector shorter than the blue vector. Then notice what happens. My projection is still running parallel to the red vector, but it's now longer. So we have to imagine that the red vector is extending out forever, and we're just trying to figure out where my perpendicular would come down and cross. So it is possible for my projection vector to be longer than the vector I'm projecting onto. That make sense? What would happen in the case that, let me make my red one longer. What would happen if I make this angle between these two vectors bigger than 90 degrees? So imagine, is this one, if I start rotating this blue one, what's going to happen to the projection vector? It's going to get bigger or smaller? It's going to get smaller, right? See it? But what happens once I get past 90? The projection vector is actually going to be on the other side. You see it? So what we have going on here is if you have a vector and you're projecting it onto another vector, that projection must be blank to that vector. What? The projection vector is what to that vector? It's a scalar multiple. It's parallel. Isn't it? It's parallel?
If it's on it, it counts as, or?
Yes. Yes. It's not like lines. You know how with lines we said that two lines are parallel if they don't intersect, but if it's the same line, then we don't really say that.
One another, it's infinite.
It's the same line, so you can't really do that. It's cheating. Okay? With vectors, it doesn't matter. Okay? You can have a vector on top of another vector, and they're still parallel. So let me restate what I just said. Taking a vector and projecting the blue vector onto the red vector, the answer is a vector, and it is parallel to the red vector. Yes? Parallel. So it's a scalar multiple of the red vector. Questions? Do you think we could project it the other way? The red onto the blue? Sure, why not? So let me move this one back, and now let me project the red onto the blue. And let me try and cheat a little bit here. So do you see where, if I project the red onto the blue, do you see where it is? What's that? Yes, but I haven't done it yet. I'm about to do it. But if I do it, do you see where it is yet? It should be 90 degrees to this blue one, so it should be perpendicular to the blue one, and it should be wherever that red one that tip would be. So it should be right here, shouldn't it? So I'll flip the projection over. And I'll draw the construction right there. There we go. All right? So this red one projected onto the blue one is the answer, the projection vector, is a scalar multiple of the blue vector in this case. Was that a question? Yes?
So that's actually another question I was asking earlier about it being component multiplied onto a component of the other vector being multiplied to it. Is that what that is? Because with the dot product, it's the angle in between the two. Between the two vectors, so it shouldn't really matter what direction. Well, I mean, if you rotate it, it shouldn't really change.
Can we discuss it after? Only because I need to make sure I understand the way you were visualizing it. The way that I understood is that you were looking at the cosine theta coming off of your standard right triangle, and that the theta you were referring to was not the same theta as that I was referring to. So let's clarify that after class so I can answer that correctly. Okay. Take the red one the other direction, it's going to point the opposite way, right? Okay, so that's the visual. Now just imagine this coming off the piece of paper and being in three-dimensional space. You can do the same thing. You can have a vector, you know, two vectors sitting out here, you put them tail to tail, and then you project this one down to this one, and you're going to have some vector here, yes? Okay. So there must be some way that we can mechanically find that purple vector, right? Like a formula. And we have it. Here it is. First of all, you have to know what vector is being projected onto what vector. So here's the notation we use, PROJ for projection. And you put the u vector here and the v vector here. If you write it this way, the u vector is being projected onto the v. So just think of the one that's subscripted as the one that you're projecting onto. All right? If this is the notation that we're going to use for it, then this is the formula. So first of all, please recognize that that's the vector v. Right? And we said that when you project the u, right, the blue one, let's say, onto the red one, your answer is a scalar multiple of the red one, yes? So when I project u onto v, my answer should be a scalar multiple of the v, shouldn't it? The scalar multiple of v. Here's v. This right here is a vector or a number? Let's see, it's a number. Let's see why. A dot product is always a number, right? Magnitude of a vector is a length, that's a number, and you square it, that's a number. So this is just a number, right? Sitting in front of the vector. This is scalar multiplication. You are scaling the vector v. This is how much you scale it by in order to get that projection vector. Understand? That's what I'm saying here. This is just a number. It's multiplied by v, so the projection is just some scalar multiple of v as we expected.
So,
Go ahead.
so u is the one you're being projected on, or the one you're projecting?
U, okay, v is being projected onto.
Okay, so the small one is always the one you're projecting.
The one down here, the one up here, u is going onto v, so it's coming down like this.
So if you flip it, it'd just be the other
If you flip it over and you were to write this, that, now you're going the v1 onto the u1. And the formula would change. How would the formula change? This would flip, but that doesn't matter because dot products you can flip anyway. This would become u, and this would become u, right? All right. Our answer is a vector, isn't it? Okay. Then you have a second type of projection, which when I was a student, I was always confused with these. I was like, what? What's the difference between these two? I don't understand the difference. And at some point, it made sense. We have something else other than a vector projection. It's called the scalar projection. All it is the length of the vector projection. So if you go back and you look at that projection thing I had here, now we said that if you project this red one, I'll do it the other way around. If you project this blue one onto this red one, that's what we have, right? And we have a formula for finding that vector. But what if all we're interested in is how long it is? If all we want is the length of it, then we call that the scalar projection. And there's a formula for it, and it's very simple to compute. So if you're trying to find the length of the vector, the projection vector, we call it the comp. It's called the component. That's what it stands for, component. It is the component of u onto v. And here's the formula. Does that look familiar? It's almost that scalar from the previous formula, isn't it? What's the only thing different? It's not squared, and it doesn't have v here. That's all it is. I'm sure I'm going to ask you, okay, this is just that same example, but it just shows you, now I'm actually showing you the projection vector, right, is a vector. Now, my computer is not real friendly. It doesn't want to do angled brackets, so it just does these little braces. So the projection vector is these angle brackets. It's a two-dimensional vector, right? That's this purple vector. And then the scalar projection is 1.9, which is, if you were to measure how long that is, it's 1.9. Got it? And you just move it around. You can change whatever. So let's not do this one because it's two-dimensional. That's too boring. Let's do a three-dimensional one. Do I have one? No, I don't have a three-dimensional one. All right. We'll just do this one, I guess. We could add another component, but let's just do this. So let's find this one. Let's find the projection of, what example? This one is v onto u. Let's do v onto u. So the definition, what is it? What is that by definition? This should be u dot v. It doesn't matter if you do v dot u, but the bottom one is important. What's the bottom one?
Absolute value.
Okay, so the magnitude of u squared, and then u. Because we're projecting onto u, right? So this should be u. So we'll need the dot product, and we'll need the length of u in order to compute this, right? So let's find the dot product of the two vectors. Dot product, -6 and 28, which is 22. I need the length of u, which is square root of 4 plus 16, which is root 20. And then I'm going to plug it in over there and square it. So here's what I've got. This is u dot v, which is 22, over the magnitude of u, which is root 20, squared, and then times u. So how do I write this? It's the vector, right? So let's just write the vector right here. 2, 4. And this is going to be scalar multiplication. There's a little imaginary dot right there, right? Not dot product, just multiplication. So that cleans up, doesn't it? What is that over there? 11 tenths. Right, because you square root 20, you get 20. Then reduce everything by 2. And then pass this constant through. 22 tenths and 44 tenths. Now it asks us also to sketch the results. Y'all want to sketch them real quick? Don't mind sketching it? It won't take long. It's two-dimensional. No questions, though? Okay, the vector u is the vector 2, 4. 1, 2, 1, 2. Shit, I'm going to run out of room. I'm going to run out of room for v because v goes way up there. So let me do this. Okay. 1, 2, 1, 2, 3, 4. So here's u. And then v is negative 3, 7. Something like that. And then I'd like us just to go ahead and sketch this vector. So what is this number here? This is 2.2 and this is 4.4, isn't it? Yeah? So let's graph that vector. 2.2 to the right, 2.2, and then up 4.4, so 4.4 somewhere around here. And now draw a vector to that point. I'm kind of moving it to the side so I don't draw it right on top of it. And what we're saying is that if you take v, which I forgot to label v, right? If you project v onto u, so project that down onto u, it's going to be that red vector. So it's a little longer, isn't it? Our projection vector is a little bit longer than the other one. How long is it? You could use the comp formula, couldn't you? But you could also just find the length of this, couldn't you? Either way. You already have this here, don't you? So you could just take squared, squared, add them together, square root. That's how long it is, right? But let's just use the comp formula so we can just practice with it one time. The component formula of v onto u would be this formula, but without the squared on the bottom. That's trash. We already said the dot product was 22, and the bottom was root 20, but no squared now. Whatever that number is, yeah? That's how long that vector is. Any questions? Because I'm going to move on. We're okay? Yes.
I was reading the book and it really helped me understand the difference between the vector projections and the scalar. It said the vector projection is the scalar projection times the unit vector in the direction of vector A.
Wait, say it again.
The vector projection is the scalar projection times the unit vector in the direction of A.
Okay.
So if you look at the formula, all you do is add the unit vector, which is the vector over the magnitude, and you get the projection.
Okay, yes, I see what you're saying. What was your name again?
What's that?
Jose. Okay, so this is what you're saying. These two formulas are the same, right?
Yeah.
And so this right here is a unit vector pointing in the same direction as u, isn't it? That's a unit vector pointing in the same direction as u, because if you take a vector and divide it by its own length, it has a unit length. So that vector points in the same direction as u, but you're scaling it by this, right? And this is the component. That's what you're saying. So if you find that more easier to understand, then that's fine. All right, moving on. Example 11. You're given a vector in three-dimensional space. You're trying to find a vector v such that the component of u onto v is 3. Okay. So I've got some vector sitting out here, bless you, in three-dimensional space, which we're calling u. And I want to find a vector v such that the component of u onto v is 3. What do I mean? What is this? What the hell is this talking about? I've got to find a vector v, right, in three-dimensional space, so that when I project u onto it, right, because this is what this means, u onto v. When I project that vector onto the vector I'm trying to find, what's 3? The length of that projection is 3. That's what we're trying to find. So I'm trying to come up with some vector. Like, let's just take, for example, that one right there. When I project u onto this one, it's going to come orthogonal right into it. And then right there, I draw a vector. And that vector needs to have a length of what? 3. But what if I would have done a different vector, like this one, right? And done the projection of u onto this one? Wouldn't it have looked like this? And that would have had a different length? You'll see that? This right here would have had a different length. I need to figure out what the vector needs to be in order to have that projection have a length of 3. So how are you going to do that?
Find v
Okay.
with the comp formula.
Okay, so whenever you have problems like this, just start writing down what it is that you're trying to do, right? The things that you know, the things you don't know. So what I want, right? I want the component of u onto v to be equal to 3. Well, what is the component of u onto v by definition?
U dot v.
This is u dot v over magnitude of v. I need that to be 3, right? Do you know any of these pieces? Like, I mean, you don't know what v is, do you? That's what you're trying to find, right? But you know everything about u, don't you? Yes. So let's start filling in some information here. I know that u, of course, was given to me to be 4, 0, negative 1. And therefore, if I call v, which is the thing I'm trying to find, v1, v2, v3, right? We want this, right? We want to know what that is? That's what we're trying to find? That if I ask you to dot these, what would you get? Because that's what the top is, right? What would u dot v be? 4 times v1 plus 0 times v2, which means it's gone, right? Plus negative 1 times v3, which is minus v3. That's what the top is, right? Then what's the magnitude of v? It's the square root of v1 squared plus v2 squared plus v3 squared. Yes? So let's go back over to this. Let's rewrite this formula again, but let's replace the top and bottom with what we just found over there. See if it gets any nicer, any easier to work with. Okay, so u dot v was 4v1 minus v3 over the magnitude of v, which was the square root of v1 squared plus v2 squared plus v3 squared. That needs to be 3, right? Now, before I proceed, let's think about this for a second. Do you think that the answer is unique? Do you think that there's only one vector v that would qualify? What do you think?
I want to say no because it's 3D.
Okay. All right, so let's say this is my vector u in three-dimensional space, right? I need to project it onto some v so that when I project this down perpendicular, right, that this length is 3, correct? So let's say this is the vector. Let's say this is it. If I project this down, that's 3, right? Okay, imagine that I keep the angle between these the same, but I spin this around like this. Do you see? Almost like making a cone. It would look like this if I were to try and draw it. Here's my v. Here's my vector u. When I project it down, I get a length of 3 here, and that's what I want, right? But if we spin that thing around, right? Wouldn't that, you know, I should be spinning the other one. Should be spinning the red one. That's too late. I have to erase it. The u can't change, can it? Pardon. U has to stay there. So u is here. This length is 3. Yes? Now take the red vector, and, the red one, and spin it around the blue one. And if you do that, right, every vector that would go around like that, they would all still have that projection length of 3, right? So there's probably an infinite number of answers. Do you see it? Okay, now how do I know that by looking at this? That there's an infinite number of answers.
Because you got so many variables for V.
How many variables do I have?
3.
3? How many equations do I have? How many equations do I have here? I only see one equal sign, right? There's no other equations that I'm working with? I mean, this is the only equation I have to work with, right? I have one equation, I have 3 unknown variables. That means you're going to have 3 variables. If you go back to college algebra, if we solved matrices, do you remember if you had like 2 equations and 2 unknowns, you would have at most, unless they're the same line, 1 solution? The number of solutions is dictated by the number of equations and number of unknowns you have. If you have more unknowns than equations, you have infinite solutions. So I just need to find one, any one that I want. So you can pick. You can just make any of these whatever you want, and that'll make the equation easier to solve. So how about we try this? How about if I let V3 be 0? Does this problem become a little easier? It becomes 4V1, right, over square root of V1 squared plus V2 squared equals 3. Now how many equations and unknowns do I have? I have 2 unknowns in one equation. So why don't I pick another one? Maybe I can do this. Let's let V2 be, you want to try 0 again? As long as I can solve what's left, I've got an answer. So 4V1 over what? Square root of V1 squared must equal 3. Right? Is that going to work? Is that going to work? Why is that not going to work? Because your V1 is basically going to cancel out. And 4 is not equal 3. So I killed off V3 on my own, right? I said V3 was 0. And then I hoped that I could make V2 0. But it turned out that I couldn't. So that vector, it's not possible to get an answer that has those components. So anyone have another suggestion? Make V1 0 and V3 0? That you can't do. Can't do V1 and V3 0 because the top will be 0, and then 0 can't be 3.
Make V2 1.
You want to make V2 1?
Yes.
You can? No, try some. Make V3 1?
What would you do?
This is what I would do. And I'd realize I can't do this, and then I would make V2 1 right now.